By the time you finished watching this video, 34 people will have died from lung cancer. This number is breathtaking, quite literally. According to the World Health Organization, lung cancer is the deadliest cancer worldwide. Each year it claims an estimated 1.8 million lives, about 18% of all cancer-related deaths globally. Welcome to Fantastic Datasets and where to find them. Today we will dive into LungHist700, a dataset of histological images for deep learning and pulmonary pathology. To understand the LungHist700 dataset, we first need a bit of medical context about lung cancer. Lung cancer comes in different forms, broadly categorized into small cell lung cancer and non-small cell lung cancer. The LungHist700 dataset focuses on the most common types of non-small cell lung cancer, adenocarcinoma and squamous cell carcinoma. According to the Datasets paper, adenocarcinomas are tumors that exhibit microscopic glandular-related tissue cytology, tissue architecture, and/or gland-related products. Squamous cell carcinomas are characterized by observable traits of squamous differentiation such as intercellular bridges, keratinization, and the formation of squamous pearls. According to the World Health Organization, the leading cause of lung cancer is active smoking. However, other factors like passive smoking, air pollution, and exposure to asbestos or other hazardous chemicals also contribute. Common symptoms of lung cancer as listed by the WHO include a persistent cough, chest pain, shortness of breath, coughing up blood, fatigue, unexplained weight loss, and recurring lung infections. Diagnosing lung cancer involves several methods, but the one that provides the most detailed insight is the examination of histological images of lung tissue. In this process, a tissue sample is taken from the patient, either during surgery or via biopsy. The sample is then embedded in wax, sliced into ultra-thin sections, and stained with contrast dyes. These prepared samples are examined under the microscope. The LungHist700 dataset is made up of exactly these kinds of microscopic images. The LungHist700 dataset was published in 2024 by Diosdado and colleagues from the Universidad de Barcelona. The researchers collected 691 histological lung images from 45 patients at the Hospital Clínico Universitario de Valladolid in Spain. The images show stained lung tissue and were captured at both 20 times and 40 times magnification. They are categorized into 3 differentiation levels: well, moderately, and poorly differentiable. Here you can see sample images from the dataset. The top row shows tissue at 20 times and the bottom row at 40 times magnification. Each column represents one of the 3 labels: normal lung, adenocarcinoma, and squamous cell carcinoma. As an untrained individual, it's nearly impossible to tell them apart, but see if you can guess which column shows the healthy lung tissue. As mentioned earlier, the samples are also labeled with subclasses that indicate how differentiable the cancerous tissue is. This applies only to the cancerous samples, since differentiation refers to how many recognizable features the cancer cells have. Looking at the 4 samples on the left, try to guess which one are well, moderately, or poorly differentiable. Feel free to pause the video and take a closer look. All of this highlights how much training is needed to accurately interpret these images, and it shows how a well-performing AI model can significantly support the diagnostic process. This table, taken from the LungHist700 paper, shows the number of samples per superclass and subclass. As you can see, the dataset is fairly balanced across categories, with a slightly smaller number of normal lung samples. The paper notes that all samples were taken from cancer patients, none from healthy individuals. That's because collecting lung tissue from healthy individuals via biopsy or surgery is expensive and potentially harmful. Working through the dataset, though, reveals that some patients have only contributed normal lung samples. One patient, number 21, was unfortunate enough to contribute samples for both adenocarcinoma and squamous cell carcinoma. The number of samples per patient also varies widely. For instance, patient 35 contributed just 1 sample, while patient 14 provided a sizable 51. When we drill down into specific combinations of magnification, superclass, and subclass, the number of contributing patients can get very low. In the cells marked red, for example, only 6 unique patients contributed to each subset. Despite this variability, the small number of patients and the fact that all of them had cancer should not introduce significant bias. That's because healthy lung cells tend to look consistent across individuals, regardless of whether cancer is present elsewhere in the tissue. The LungHist700 paper also includes a baseline classifier to benchmark future models. The authors used the ResNet-50 architecture pre-trained on ImageNet combined with the Atom Optimizer and various data augmentation techniques. They trained separate classifiers for each magnification level, 20 times and 40 times, effectively splitting the dataset in half. All implementation details are provided in the paper and the corresponding GitHub repository. The experiments have also been independently reproduced. Here you can see the confusion matrix for the 20 times magnification baseline classifier. The abbreviations ACA stand for adenocarcinoma, NOR for normal lung, and SCC for squamous cell carcinoma. In this matrix, rows represent the true class labels, while columns show the model's predictions. The classifier performs well when identifying adenocarcinomas and normal lung tissue. However, its accuracy drops significantly when classifying squamous cell carcinoma. It's worth noting that the performance of the published baseline did not match that of my self-conducted reproduction. The reproduced model achieved significantly higher accuracy. This discrepancy could be due to minor implementation differences, such as library versions, or more likely a different data split for training, testing, and validation. For consistency, we'll use the published baseline as our point of reference. When we look at the 40 times magnification baseline results, we see similar trends. Both the 20 times and 40 times magnification models perform comparably across classes, with the 20 times model slightly outperforming the 40 times magnification model. That said, both models struggle with squamous cell carcinoma. This is especially concerning in a medical context, where misclassifying a sick patient as healthy could delay treatment and reduce their chance of recovery. One major strength of the LungHist700 dataset is that it includes subclass labels indicating how differentiable the cancer's tissue is. This allows us to investigate how classification performance changes as differentiation decreases. Here, we evaluate the test performance of the reproduced 20 times magnification baseline classifier across each subclass. It's important to note that this analysis leaves us with relatively few test samples, which could bias the results. Still, we observe that the classifier performs very well on well and moderately differentiable samples, even for squamous cell carcinoma, which has been harder to classify overall. However, performance clearly drops on poorly differentiable squamous cell carcinoma samples. This is a valuable insight as it suggests that the level of differentiation can act as a measure for prediction confidence. The FAIR principles were introduced in 2016 as a guideline to help datasets support scientific progress. In this section, we'll evaluate the LungHist700 dataset according to these principles. The first principle, findability, is fulfilled. The dataset has globally unique identifiers. Accessibility is also satisfied. The LungHist700 dataset is freely available without the need for authentication, and the Apache License 2.0 allows for free use, modification, and distribution. The third principle, interoperability, is met as well. The metadata is provided in CSV format and the images are in JPEG format, which makes it machine readable. Finally, reusability is only partially fulfilled. The metadata includes just a few fields: superclass, subclass, resolution, image ID, and patient ID. While this is helpful, it lacks deeper contextual details, such as information about the microscope or scanning settings, which would enhance reproducibility and reuse. The LungHist700 dataset fits well into the broader ecosystem of lung cancer datasets. Many existing datasets focus on screening methods or symptom-based data for various types of lung cancer. The most comparable dataset to LungHist700 is the lung and colon cancer histopathological images dataset available on Kaggle. It includes an even wider range of cancer types beyond just adenocarcinomas and squamous cell carcinomas. Looking ahead, the LungHist700 dataset can be used for interesting applications. One direction would be to reframe it as a segmentation task, not just predicting the cancer type, but also identifying how far cancerous cells have spread across the sample tissue. Another potential direction is developing a magnification agnostic approach. The current baselines only use data from a single magnification level at a time. A magnification agnostic model could leverage more data for training, validation, and testing, and make it easier to combine LungHist700 with histological data from other datasets. Finally, we could explore predicting the subclass in addition to the superclass. As we've seen, subclass labels offer a useful measure for the model confidence. In medical applications, providing a confidence measure is not just helpful, it's essential. With datasets like LungHist700, there's a real potential to slow the rise of this number. And since the dataset is openly available, you can be a part of that change.